Hello guys, welcome back to another video on my channel. It's been a while. In the last video, I proved the Ramanujan master theorem using G.H. Hardy's proof, which was the most rigorous and satisfying that I had on my hands at that time. There were some comments, there were some questions, and I'm just gonna say in this video, I'm gonna do the applications of Ramanujan's master's theorem and why that theorem is even called the master theorem, and you'll see why exactly by the end of the video. But let me just tell you this, that in this video I'm not gonna actually get into the nitty-gritty analysis details of the region of conversion, which is the real part of S that we have in the original form that we wrote down. I'm not going to get into the details. The integrals or the applications we're going to be doing as a result of the master theorem are well-known examples. So the analysis has been worked out in research papers, and moreover, the conditions that I gave in the last video, that G.H. Hardy gave actually, are not the strongest, and they're not the weakest. You can weaken them further, or you could even strengthen them. For strengthening is not helping anyone. You could weaken them further. You could actually weaken Ramanujan's natural assumptions in quotes even further as well. So it's really up to you to analytically extend or do some sort of regularization to extend the domain of validity compared to the original. Anyways, so let's get started. Let's just recall the Ramanujan master theorem. So if we have an integral of x to the s minus 1 of the sum from k equals 0 to infinity of function lambda of k over k factorial times minus x to the k dx, that's given as gamma of s times lambda at minus s with the appropriate region for convergence, which is basically given by the real part of s. Now, we're going to have to choose such a region such that this gamma function and gamma of minus s is analytic and well defined everywhere in that kind of region of convergence that we choose. And that's something we're going to naturally sort of inculcate throughout our examples. And as I said, I'm not going to get into the details. These are well-known results. So the first case is, let's take a greater than 0, and then f of x is e to the minus x, which we can easily write as the simplest Taylor series expansion that you learn about in calculus class. So f of x is sum from k equals 0 to infinity a to the k minus x to the k over k factorial. And this basically fits the form of the sum that we had here inside this integral, the sum from 0 to infinity of lambda of k over k factorial. The only thing is the lambda in this case is everything apart from the k factorial. So that's going to be a to the k because we already have a minus x to the k. So a to the k is going to be lambda of k. And, we can just plug in using the formula, using the RMT. That's what I'm going to call Ramanujan master theorem. So we have integral 0 to infinity x to the s minus 1 e to the minus ax dx gives us gamma of s over a to the s. That's not surprising. You would say, well, we knew this. This is just the integral definition of the gamma function. But this is a nice way of actually confirming that the formula actually makes sense. This is, you can call it the first sanity check. Although we didn't really argue strongly for what real part of s is going to be, but knowing the properties of the gamma function, it's analytic on the real part of s greater than 0, which can be analytically continued further, but let's leave it at that. Also, for a greater than 0, we have 1 plus x to the minus a, which we can write as a Taylor binomial expansion. So 1 minus ax plus a plus 1 times a over 2x squared, so on, which we can write all these terms nicely as k plus a minus 1 choose k. In the sum, k goes to 0 to infinity of minus x to the k, because that's flipping the signs. We can really nicely write these combinatorial factors in terms of gamma functions, actually factorials, which can be written as gamma functions. So we have gamma of k plus a over gamma of a minus x to the k over k factorial in a sum from 0 to infinity in k. So we apply Ramanujan's master theorem with lambda of k given by gamma of a plus k over gamma of a. And then we have integral from 0 to infinity x to the s minus 1 dx divided by 1 plus x to the a. That gives us gamma of s times gamma of a minus s over gamma of a, which actually, either looking at the integral representation or this quantity, this distribution of gamma functions on this right hand side, is actually just the beta function of s comma a minus s. So I mean, this also can be treated as a sanity check in this regard, because this is not something exotic, but there's much to follow after this. Hypergeometric functions. Yes, I can hear the people in the comment section saying you're finally talking about these guys. These guys are very powerful. You can write most functions in terms of these guys. You can generalize a lot of things with them, and you'll see why. So let's define PFQ of C semicolon D semicolon minus X to be, and this is the standard definition using infinite series, sum from k equals 0 to infinity, C1 sub k, C2 sub k, dot dot, or Cp sub k. So the p is for how many of these C coefficients there are in the numerator, divided by d1 sub k, d2 sub k, dot dot dot, dq sub k. So the q is for how many coefficients there are in the denominator, times minus x to the k over k factorial. So this last term is basically sort of going to be a given in all the functions expansions that we're going to consider, because this just goes nicely into the master theorem. The only thing we need to clarify is this subscript k. What is this notation? Don't get intimidated. It was intimidating, I'm not gonna lie. So ai sub k is actually ai times ai plus 1 dot 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 ai plus k minus 1. So it's like a reverse factorial basically, because you're increasing a power, but you're not going infinitely high. Otherwise it would diverge. You're going until k minus 1. So all in all, there's like k terms in this product. And this can be nicely written as gamma of, I think there should be ai there. Sorry about that. ai plus k divided by gamma of ai. There you go. Okay. And this is actually called the Pochhammer symbol. Sorry if I butchered the name. Okay, moving on. We identify that we can replace all of these coefficients using the gamma function. So we just get a potpourri of these gamma functions. So lambda of k equals gamma of c1 plus k, gamma of c2 plus k, gamma of cp plus k divided by gamma of d1 plus k, d2 plus k, gamma of dq plus k, and then just the non-k terms on this second product. So gamma of d1 dot 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 gamma of dq, gamma of c1 dot 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 gamma of cp. So from 1, which is Ramanujan's master theorem, we have the Mellin transform, or the integral from 0 to infinity x to the s minus 1 of pfq cd minus x dx to be gamma of s, gamma of c1 minus s dot dot gamma of cp minus x divided by gamma of d1 minus s, gamma of dq minus s, gamma of d1, gamma of dq, gamma of c1 dot dot gamma of cp. So it's quite an elaborate expression. I mean, you'd say this is quite abstract. I mean, this works for this one kind of functions, but I said that most function can be expressed as these hypergeometric functions. So the first candidate for such an expansion, and this is probably the second most useful formula in today's video, apart from obviously Ramanujan's master theorem, The first candidate is the error function evaluated at x, which is defined as the integral from 0 to x e to the minus t squared dt with a normalization factor of 2 over square root pi. We can write this as an infinite series, just expand this and then integrate term by term. 2 over square root pi, sum from k equals 0 to infinity, minus 1 to the k over k factorial, x to the 2k plus 1 over 2k plus 1. And then we can actually just take some terms outside. So we can take a minus x squared whole thing to the k, but we are also taking an x outside because there was a 2k plus 1. So we have taken a 2x over square root pi outside. We have minus x squared whole thing to the k divided by k factorial times 2k plus 1 in a sum from 0 to infinity in k. Now, what's the next step? We're going to write 1 over 2k plus 1 in terms of the gamma function. So 1 over 2 times 1 over k plus 1 half, which is 1 over 2 times gamma of k plus 1 divided by gamma of k plus 3 halves. And, we can just break apart these gamma functions because in the sense we're just going to insert a 1/2 factor and a 3/2 factor and divide by those. So 1/2 gamma of k plus 1/2 divided by gamma of 1/2 times gamma of 1/2, so those two will cancel, over gamma of 3/2 times gamma of 3/2, so those two will also cancel if you want to equate that to the original, divided by gamma of k plus 3/2. Advantage of doing that is we can rewrite this as the Pochhammer symbol. So 1/2 sub k divided by 3/2 sub k times gamma of 1/2 divided by gamma of 3/2, which is, all this, the 1/2 will cancel. So we just get 1/2 sub k divided by 3/2 sub k. So the error function, by virtue of, rewriting this in terms of the Pochhammer symbol, is just given by 2x over square root pi 1f1 1/2 3/2 minus x squared. Now 1f1 is actually a special hypergeometric function. It's called a confluent hypergeometric function. But let's leave the names aside. What matters is the integral we're going to get as a byproduct of the RMT. So integral 0 to infinity x to the s minus 1 error function of f of x dx is equal to minus 1 over s times square root pi gamma of 1 plus s over 2. So this is probably the first non-trivial integral, which is, not completely abstract, that we're doing today. Fair enough. Moving on, since we have a lot to cover in this video, the Bessel functions. The Bessel functions are solutions of a particular differential equation. They appear in the cylindrical Laplace's equation for the radial part, if I'm not wrong. And they have certain properties in terms of like Sturm-Liouville theory. But in this case, we just care about the definition in terms of the power series. So J nu of x is defined as x over 2 to the nu sum from k equals 0 to infinity minus 1 to the k divided by k factorial times k plus nu factorial x over 2 to the k. Which now the derivation of how we go from this to the hypergeometric function is probably the fodder for another separate video. Maybe I'll make that in the future. For now, let's just take this as a given. 1 over gamma of nu plus 1 x over 2 to the nu 0 f1, and since there's a 0, there's no first argument here, we can leave that empty, nu plus 1 minus x squared over 4. Okay, so that's simple. Since we know we've written it in terms of the hypergeometric function, we can just use the formula that we derived for the applying RMT on hypergeometric functions. We get integral 0 to infinity x to the s minus 1 j nu of x dx is 1 over 2 to the nu gamma of nu plus 1 integral 0 to infinity x to the s plus nu minus 1 0 f1 nu plus 1 minus x squared over 4 dx. With the substitution t equals x squared over 4, we can go and get 2 to the s minus 1 over gamma of nu plus 1 integral 0 to infinity t to the s plus nu over 2 minus 1 0 f1 nu plus 1 minus t dt, which we can simplify using the RMT. to give us 2 to the s minus 1 gamma of s plus nu over 2 divided by gamma of nu minus s over 2 plus 1. I'm skipping a lot of steps, but this, these are well-known results from literature. The point of this video is to demonstrate these results, to let you know how powerful the RMT is, and also to, generate some new integrals, which also happen to be Mellin transform. So this expression is actually the Mellin transform of the Bessel function. It would probably have taken like a separate video, like a separate CD, like a couple of videos on its own if I sat down to like compute without RMT. But just knowing how we can write in terms of the hypergeometric function, and we just do it in a few steps. Moving on to the Digamma function. First of all, the Digamma function involves the kth harmonic number. So the kth harmonic number is actually Euler-Mascheroni plus Digamma of k plus 1. We're going to need one formula that I actually proved in one of my very old videos. I think one from 2020. So natural log of 1 plus x over 1 plus x is equal to minus sum from k equals 1 to infinity of the kth harmonic number times minus x to the k. Now you see the minus x to the k, that's valuable. We're going to need that. We're also going to need a factorial. But since we're interested in a digamma, let's write digamma of k plus 1 as minus x to, times minus x to the k. We introduce the k factorial, but we also have to introduce it in the numerator, k factorial, sum from 1 to infinity, which can be expressed using the Euler-Mascheroni and the harmonic number as sum from k equals 1 to infinity minus x to the k times the kth harmonic number minus Euler-Mascheroni, which can be written as, now with the Euler-Mascheroni, it's a constant, so the only thing we're going to have is an infinite geometric series in the minus x to the k. So that sums up to be x over x plus 1. So I'm going to take an x plus 1 over x plus 1 outside, because we're going to have that with the hk as well. We're going to use this formula for the hk. So we have the 1 plus x in the denominator come outside, times gamma of x minus, and the numerator has a natural log. So natural log of 1 plus x. Fair enough. Moving on. We can write the k factorial as gamma of k plus 1, and then we just sum from 0 to infinity, gamma of k plus 1 digamma of k plus 1 minus x to the k over k factorial. And we have integral 0 to infinity x to the s minus 1 dx, which using RMT is just gamma of s, gamma of 1 minus s, digamma of 1 minus s equals pi over sine of pi s times digamma of 1 minus s. Okay. And then we get Euler-Mascheroni integral 0 to infinity x to the s over 1 plus s dx minus integral 0 to infinity x to the s minus 1 natural log of 1 plus x over 1 plus x dx, which is basically the right hand side in this equation. I'm just writing in terms of the integral because we wrote the left hand side. The first term is a well-known Mellin transform. I actually proved it using contour integration in one video. So we have Euler-Mascheroni pi over sine of pi s plus pi minus integral 0 to infinity x to the s minus 1 natural log of 1 plus x over 1 plus x dx, which is the integral we're interested in. So we just make that the subject of the equation. Integral 0 to infinity x to the s minus 1 natural log of 1 plus x over 1 plus x dx is going to be taking the sign on the other side. So we have minus pi over sine of pi s times Euler-Mascheroni plus digamma of 1 minus s from, this, using this and as well as this. So with the special case occurs when s equals 1/2. Then we have integral 0 to infinity natural log of 1 plus x over square root x times 1 plus x dx equals minus pi times gamma of digamma of 1 by 2. So it's a very nice looking result. It has the Euler-Mascheroni and the digamma function. We also have integral 0 to infinity digamma plus natural log of 1 plus x divided by square root x times 1 plus x dx equals pi times Euler-Mascheroni plus 2 times natural log of 2. This is, if we sort of plug in the particular value of the digamma. With the substitution, this becomes integral 0 to infinity natural log of 1 plus t squared over 1 plus t squared dt, which turns out to be pi times natural log of 2. And also, this can be is equivalent to integral 0 to pi over 2 natural log of sine x dx, which is just minus pi over 2 natural log of 2. So that's the sanity check for this general result that we had. These are some of the most nice looking results ever, but that's the magic of Ramanujan. Moving on to the natural log of the gamma function, for which we need the Weierstrass representation of the gamma function. So gamma of x is e to the minus Euler-Mascheroni x over x, product from 1 to infinity in n, 1 plus x over n to the minus 1, e to the x over n. And we also are going to need this representation of the digamma function. Digamma of x plus 1 equals minus Euler-Mascheroni plus sum from n equals 1 to infinity, x to the n minus 1 to the n plus 1, Riemann Zeta of n plus 1. So you can call this the Taylor series expansion because we have an x to the n term appearing, which is minus Euler-Mascheroni of n plus sum from n equals 2 to infinity, x to the n minus 1 minus 1 to the n, Riemann Zeta of 2. And we also know this integrating both sides, because the digamma is just the derivative of the natural log of gamma. So we can just take the antiderivative on both sides. Natural log of gamma of 1 plus x equals minus Euler-Mascheroni times x plus sum from n equals 2 to infinity minus x to the n over n, Riemann Zeta of 2. Just add this Euler-Mascheroni times x to both sides and divide by x squared. So we get natural log of gamma of 1 plus x plus Euler-Mascheroni x divided by x squared equals sum from k equals 0 to infinity minus x to the k over k factorial times lambda of k, where lambda of k is gamma of k plus 1, Riemann Zeta of k plus 2 over k plus 2. So just plug it into RMT now. Integral 0 to infinity x to the s minus 1 natural log of gamma of 1 plus x plus Euler-Mascheroni of x divided by x squared dx is pi over sine pi s times Riemann Zeta of 2 minus s over 2 minus s. So it has a nice looking result with the Riemann Zeta function popping up from the gamma function, and which is valid on the region 0 less than real part of s less than 1. So it's that 0, 1 strip. Special case happens when s equals 1/2 and s equals 3/4. So for the 1/2, we have integral 0 to infinity natural log of gamma of 1 plus x plus Euler-Mascheroni x divided by x to the 5 by 2 dx equals 2 pi by 3 Riemann Zeta of 3 by 2. Yeah, and for the other case, we have integral 0 to infinity natural log of gamma of 1 plus x plus Euler-Mascheroni x divided by x to the 5 by 4 equals 4 over 5 times square root 2 pi times Riemann Zeta of 5 by 4. So here are some interesting looking results. I'm guessing if you want to compute the value of the Riemann Zeta, you could run some numerical simulation on this integral. But the main point is Mathematica 7 cannot really evaluate these. So if you put them into Mathematica 7, which was the claim of the literature I was sourcing, they claim that Mathematica 7 cannot evaluate these complicated looking integrals. Anyways, moving on to the digamma now. Digamma of x plus 1 is minus Euler-Mascheroni plus sum from k equals 1 to infinity minus 1 to the k plus 1 Riemann Zeta of k plus 1 times x to the k. We do a similar procedure. So what we're going to do is we're going to take the Euler-Mascheroni, add that. So digamma of x plus 1 plus Euler-Mascheroni over x, so we divide by x as well, gives sum from k equals 0 to infinity, Riemann Zeta of k plus 2, gamma of k plus 2, times minus x to the k over k factorial. So the gamma of k plus 1 is basically cancelling the k factorial because that wasn't there before. And this nicely fits into the RMT form for lambda. So we have integral 0 to infinity x to the s minus 1, digamma of x plus 1 plus Euler-Mascheroni over x dx equals gamma of s, gamma of 1 minus s, Riemann Zeta of 2 minus s. So the first can be simplified using the reflection formula pi over sine pi s times the Riemann Zeta of 2 minus s. Special cases again for s equals 1/2 and s equals 3 by 4. Integral from 0 to infinity, digamma of 1 plus x plus Euler-Mascheroni over x to the 3 by 2 dx is pi times Riemann Zeta of 3 by 2. Integral 0 to infinity, Euler-Mascheroni 1 plus x plus digamma of 1 plus x plus Euler-Mascheroni divided by x to the 5 by 4 dx is square root 2 times pi times the Riemann Zeta of 5 by 4. So these are, I think, are all the integrals I had for today. It's a tad bit long, but I think this should more than prove the point why Ramanujan's master theorem is indeed a master theorem. It's called a master theorem. Usually it's a big thing when a theorem is named after someone. It's a huge honor. But they've also gone ahead and called it a master theorem as if it's the mother, it's the generator of, all these other nice identities which do well for Ramanujan's legacy in terms of what he used to do. He used to have complicated functions inside expressions. And that's what these integrals show as well. You have digammas, you have confluent hypergeometric functions and Riemann zetas. What else do you want? I feel this is a culmination of all the things we've done so far on this channel since 2020, because we actually did use some of the results involving the harmonic numbers. Yeah. So I think I'm going to end this video here. Thanks for watching, guys, and please subscribe to my channel if you haven't before, and like and share my videos. Peace out in the meantime.